find an optimal control U that minimizes a cost function G. And this control, it is the input. So we have the input of a system, or described by differential equations. And here we have X. Here you have a system, differential equation. We have an input, and we have a state or a variable. I can call it X, I can call it Y, I can call it Z. So if you want, you can call it Z dot to avoid so this input, for example, this is the time, and this is the input. So here in red is Z, and in blue I will draw U. So we know we have a nonlinear function. So here a nonlinear equation, describing the dynamics of the system. So if I put an input here like this, for example, I have the time here, final time TF, and here initial time. So here I have 1, 2, 3, 4, 5. So I have five steps, for example. 5 steps. So this is the input that is entering on the system. So I will draw it again here. So for example, this is U. Okay, so this U is, as you see, is piecewise continuous. So this input, I will put it here. The system starts from an initial point. For example, let us take, we have only one Z, so scalar system. So we will get a solution. For example, here it is X at time 0, and the evolution of the system maybe something like this, I don't know. Okay, so this is here, it is Z at T final, and here Z at T initial, so at T0. So in order, so this is, we have a system. Our idea is to find this optimal sequence such that I minimize a cost function. So we are solving an optimization problem. Minimize J. So we want to find this input U that minimizes a cost function. Why it is an optimization problem? First of all, we have a cost function to minimize, and we have, as usual, constraints, subject to constraints. What we will find in these constraints depend on the problem. We, first of all, maybe there are U max and U min. So here, we cannot go beyond U max and umin. So first of all, there are constraints on the input. We may have also constraints on the state. For example, on the state, I will, as I call it, Z, here U. This cost function may be, it depends on Z, or on U, or on Z and U, or maybe it depends on Z final and time final, and so on. So as you see, we have an optimization problem. We want to minimize, we want to find the optimal sequence of U that minimizes J, but in addition, we have this dynamical system or differential equation, and we have to use this dynamical equation in order to calculate maybe the constraints on U or on Z or to calculate J. Can use, for example, a function that is called ODE, maybe 45, 20, it is depending on the technique of integration, but there are in Matlab functions like ODE that we can use to integrate systems. So this is the first thing. Now, in order to solve this problem, because it is nonlinear optimization, we can use fmincon. So here we can put the cost function. So cost function. We can put linear constraints. So when I say linear constraints, it is, you have to remember we have two types, equality and inequality constraints. So equality constraints, maybe we have ax less than equal to b exactly. So we have linear relation between the decision variable, here it is u, so here u, and some a and b, or we have a inequality times the decision variable less than inequality. So here we have linear constraints, and we can also put non-linear constraints. So also we have here equality nonlinear constraints and inequality nonlinear constraints. Okay? So as you see, we have in the fmincon or this solver or this optimizer, we can program something related to the cost function. We have these linear constraints, equality and inequality, and we have also, we can put the nonlinear constraints. And also we can put the constraints on X, upper bound, and lower bound. You will see when you read the documentation. So mainly we will use ODE and we will use fmincon. So we have x1 dot equal u, and we have x2 dot equal this 1 plus u square. Okay? And so this is our dynamical system. As you see, it is nonlinear because we have square root and we have square here. And so the idea is how you want, I want from you to know how to integrate this using ODE. So the first step, you have to know how to use ODE. Now, the second step is to understand what are the constraints. Here, we have to minimize, so we have to find U that minimizes this cost function, J, and this cost function is given by this expression. So it is from 0, so time 0 equals 0, and final time equal 1. It's just normalization. And we want to minimize this integral x1. So the integral of the first state, or the integral of U. There are many ways to code this, but I will let you do it yourself. So the idea, we want to use fmincon. Just I will have to give you also the constraints. So subject to the x at t final equal this value transpose. So the idea is we want to find the optimal sequence of U between 0 and 1 second, such that I will take this system from 0 to 0 pi over 3. Okay? So you have to code this in using, so use fmincon to code this function. So you have to know how to code this cost function. So if I give you this input in red, we will use ODE to evaluate this x, and then I will integrate. So the integration, if I use this piecewise continuous, it will be simple. It is the surface. So here we will have the time. So for example, this is final time. So we have here, I don't know, dt, 2 dt, 3 dt, and so on. Okay? And dt maybe is 1 over n. And n is the number of samples. So fmincon, if you want, we have to initialize fmincon. So fmincon, we will initialize it with U initial. I will call it U0. So for example, this sequence, we will use U0 to evaluate this G. So we will have G0. We will see if the constraints are verified or not. If they are verified, okay, I will save G0 and I will return, so Matlab will return here. And instead of using U0, we will use U1, which is a small variation of U0. We will use fmincon and we will generate another cost function. If this cost function is okay, we will save it. We will continue, and so on. Now, at the end, we will have a lot of iterations. I don't know, it depends on what we put by default or what we can impose. We will get a lot of G, and we will see which one is the best one or the minimum one. Why? Because our objective is to minimize. So imagine that it will be the iteration number 500. So Matlab will give me this cost function and the U at iteration 500 that minimizes this problem and verifies the constraints and the optimality conditions also. Okay. So I will explain for all of you. I will show you the code, one of the codes, and I hope it will work. Okay. So I will try explaining. So as usual, the initialization part. Here are some global variables. We will see global variables. We see variables. So here I use t is the number of the final time, and n is the number of samples. Okay. So samples of the input u. Here the initial point, and here is the final point. I will give you this code by the chat. Okay, final point. Here I will start with the initial input sequence. The differential equation. So x dot equal u and x dot 2 equals square root of u. Here the input of the function, the time, the state, and u, the vector of u. So here at each time we will select the good sequence of u. Here is one way to construct this sequence. So one way of construction of u. So here, for example, if the time we are at 0, we'll take the first element. If the time is greater than this, we will take the vector, and so on. Okay. Here, the cost function that we want to minimize. So as you see, we want to find x1. So we will integrate with this u between 0 and the final time using the same initial conditions. And we can use this trapezoidal integration in Matlab. So it is the integration between the time t and x. So from 0 to 1, and this is x1. This is the constraint function that we will use. We want to go from x0 equals 0 to x final at this value. Again, here we want to integrate. So we will integrate. We will calculate the initial point, and then we don't have inequality constraints. We don't have inequality constraints, but we have equality constraints. So the first one, here we have x1 minus 0, and here we have x2 minus p over 3. And we will put this in this variable. So what will be returned from this function is the equality constraints that are non-linear and the equality constraints that are non-linear. So here we have constructed the non-linear constraints. We have constructed how to calculate the cost function. Here we did how to choose for each time the appropriate sequence of control. Here we prepare the dynamical system or the differential equation. We put everything in fmincon. So the cost function, the initial guess, if you want here, it is initial guess. We can make random later if you want. Here we don't have we don't have linear equality constraints and linear inequality constraints and no bounds. And here we call this function nonlinear constraints, which is written here. If I run everything, let us see what we will get. So I will run. We will find that we are in a local minimum. So we go from 0 to 0. This is the input that is used to solve this problem. And here from 0 to pi over 3. So this is the sequence of control that optimizes this thing. As you see here, for example, we have the input that is between these values. Suppose that the input that we want to use is bounded between minus 0.4 and plus 0.4. What we will do, we have to change here. So let us see the documentation of fmincon. So we have to put lower bound and upper bound. So here we have to put, for example, so minus 0.4 times ones. So it is ones. And what is the size of, okay, ones, 1n. And the upper bound, if I put 0.4 times ones, again, 1 and n. Okay, let us run to see if it will work. It will give me an optimal control that minimizes the cost function, and in the same time, it is bounded between minus 0.4 and 0.4. Let us see if it will work. Look what we will get. So as you see, it is between minus 0.4 and 0.4. If I put random here, rand, so each time I randomize, maybe we'll get different. As you see here, each time we'll get different sequence, but this sequence will solve the problem. Okay. Look now, if I put 20 steps, what will happen? So I am getting richer value. Look, this is the control. So we are looking at the terminal value here. We start at 0 and we go to 0, and here from 0 to pi over 3. And this is the control. So if I start again, maybe you don't need 20 samples. As you see, just by this code, we can test many things. It is busy. Yeah, here, for example, another sequence, maybe it is, we started far from the, and so on.